Good. So we're going to be continuing with our review. Section 0.2, integer exponents and scientific notation. So 2 with a superscript of 3 means we're going to raise 2 to the power 3. So 2 is called the base and 3 is the exponent. And it just means that we're going to be multiplying 2 the base 3 times. And so we would get the number 8. Okay, so suppose that my base b is not equal to 0. Then I will define b to the 0 as equaling 1. Let me define natural number exponents. So suppose I have some base b, then b to the first is defined as b. b to the n plus 1 is defined as b times b to the n for any natural number n. Let me define integer exponents. So we've already defined whole number exponents. Suppose we have a negative integer exponent. So suppose I have b to the negative n, and that's defined as 1 over b to the n, where n here is a natural number not equal, and b is not equal to 0, so that I do not divide by 0. Let me give you some properties of exponents. So the first property is if I have the same base b and I'm multiplying, then I keep the base b and add exponents. In this case, let me just assume that when I'm saying equal, what that means is that either both sides of my equation exist and are equal, or if one side of the equation doesn't exist, then neither does the other side. Okay, so suppose I'm taking the ratio of two quantities. Since I have the same base, then I keep the base and subtract exponents. If I have a base to a power, I keep the base and multiply exponents. Next, if I have two different bases and I'm multiplying, but the exponents are the same, then I just raise the product of those bases to that mutual exponent. Similarly, if I have the ratio of two differing bases to the same exponent, then I take the quotient of the bases and raise that to the mutual exponent. Of course, just to be explicit, remember I'm assuming that either both sides of my equation exist, or if one side doesn't exist, then the other side doesn't. If b were 0, then neither side of this equation would exist. Again, as above, let's b to the first is b to the 0 is 1, so long as the base is not 0. In this case, I have to be explicit because 0 to the 0, I don't know what that is. Similarly, 0 to the power m is 0, so long as m is not as long as m is greater than 0. b to the minus m is 1 over b to the m. So, scientific notation. In science, sometimes we deal with very large numbers, such as suppose I want to determine the age of the universe in Planck time. So Planck time is the smallest unit of time that we know of. And so it would be 8 with a whole bunch of zeros. So just 8 followed by lots and lots and lots and lots of zeros. And so that's a very big number. So you could also have very small numbers, like 0.000 with a whole bunch of zeros, and then maybe a 1 or something. So every real number can be written in the form a times n to the times 10 to the n, where a is a number between 1 and 10. It could be 1, but it can't be 10 in absolute value. And n here is some integer. So with that, I can just say more easily, the age of the universe in Planck time is 8 times 10 to the 60 Planck time. So if you actually counted out all these zeros, there are 60 zeros. So let's do some examples. On page 24, actually let me give it a little bit more space here. I can do this. On page 24, let me do problem number 15 and then problem number 16. Write each number or expression without using exponents. So for problem 15, I have a negative 5 squared. So this means take 5, multiply it twice because I have an exponent of 2, and then negate. And so this is equal to a negative 25. And that is your answer. Let's do negative 5 squared. And so you notice these are very similar, but they're not the same. This says take negative 5 and multiply it together twice. And so negative times negative would be positive. And so my answer is a positive 25. Let me do problem number 26. Write each expression using exponents. So 2a times 2a times 2a is going to be, well, 2 times 2 times 2. So 2a times 2a times 2a, well, that's 2a cubed, which is 2 cubed times a cubed. And so I'll write this as 8a cubed. I could have left it in the second form, but usually if we can evaluate something like 2 cubed, because it's a nice small easy quantity to compute, we usually compute it. So 8 cubed. Okay, so let me do problem number 48. Okay, 1 second. Okay, so simplify each expression, write all answers without using negative exponents, assume that all variables are restricted to these numbers, to those numbers for which the expression is defined. Okay, so you're just assuming that everything's nice and defined. So let me raise each of these to the power 6. And so this is just x to the power, well, 3 times 6 is 18. Z to the power 4 times 6 is 24. And that is your answer. Let me do problem number 80. So first, let me simplify things. So 12 divided by 4 is 3. Let me bring the negative exponent down. Let me bring this negative exponent up and this negative exponent down. So if I have negative exponents, I will interchange between numerator and denominator. So this x to the fourth goes to the denominator. This y cubed goes up to the numerator. And this z to the fifth, how symmetric, goes down to the denominator. So this is equal to, let me get some more room here. Let's simplify this first. So I have y cubed times y cubed is y to the 6th. X to the 4th times x to the 4th is x to the 8th. Z to the 5th times z to the 5th is z to the 10th. Let's raise everything to the power 27. To the power 3. I was computing 3 cubed. 3 cubed is 27. Y to the 6 cubed, well, 6 times 3 is 18. Over x to the 8 times 3 is 24. And 10 times 3 is 30. And that is your answer. Let me do problem 100. Express each number in scientific notation. So, to do scientific notation, you determine the leftmost digit, leftmost non-zero digit. 2. Put a decimal. Write every digit, ending at the rightmost non-zero digit. And then you go times 10 to the power. And let's figure out how many places we had to move. Well, we had to move 1, 2, 3, 4, 5, 6, 7. And that is your answer. Let me get a little more room here. Okay, so let me bring this down. So that's your answer. Express each number in scientific notation. Okay, so let's do this. So this is a negative. Determine the leftmost non-zero digit, 8. Put in decimal point. Continue to write every digit until you get to the rightmost non-zero digit. Times 10 to the power. Well, in this case, let's bring it 1 down. This is going to have a negative exponent because this is a decimal. It's a small number. So small numbers, meaning numbers less than 1 in absolute value, have negative exponents, whereas big numbers have positive, meaning numbers bigger than 1 in absolute value, have exponents that are greater than or equal to 0. Okay, so if I have a leading 0, and this is what makes it nice, then I just count the number 0. So 1, 2, 3, 4, 5, 6, 7, 8. So this is 10 to the negative 8. So my answer is 8.9 times 10 to the negative 8. Okay, so let me, oops, I don't think I need that. Let me simplify this. So first, let me write this number, this small number, 0.0035 as 3.5 times 10 to the 2, 4, 6, 7. 170,000 as 1.7 times 10 to the 5. 1, 2, 3, 4, 5. And that's right, 85. The 0.0085 is 8.5 times 10 to the power 2, 4, 6, 7. Oh, 7. Okay. So first notice that let's just do 3.5 times 1.7 over 8.5. So only the numbers without the exponents times 10 to the power. Well, let's figure that out. Well, the 10 to the negative 7s cancel, so this is just 10 to the 5. First off, 8.5 divided by 1.7 is 5. So let me simplify this. So this is equal to, well, 3.5 divided by 5 is 0.7. And so, moving your decimal, and so this is equal to 7 times 10 to the 4. Since you had to move your decimal place over 1. So 70,000. And that's your answer. And so that is the end of section